Welcome back, everybody. So last time we introduced a couple statements about the Lie Skein lasagna module. Again, once we're sort of working with the Lie theory, I just want everything to be over Q. In that case, the lasagna module is generated by pairs of second homology classes. And so for any single second homology class, we can define an S invariant to be the filtration level of one of these Lie generators, in particular the one where, well, we take the second guy in the pair to be 0. So today, I just want to start, so there is a sort of general, there is a general result about sort of gluing some four manifolds together along a common boundary, and I don't want to try to write that all out. Maybe, if there's time at the end, I can sort of draw the large picture. But I want to highlight just a couple sort of corollaries that come from sort of the general statement. The first one maybe kind of gives the best picture of what the gluing result ought to look like. So a corollary of sort of this general sort of gluing statement is that if you have a knot that is in a framed concordance, or everything's sort of framed here in these Skein lasagna modules. If you have a framed concordance from K to K prime, then the two handle bodies xk and xk prime satisfy, well, their Lie lasagna modules are equivalent as filtered spaces. Or, if you prefer, maybe the easier thing to write is that they have the same Rasmussen invariance. Where, so technically, H2 of this guy is only isomorphic to H2 of that guy, and the isomorphism is carrying alpha to alpha prime here. Okay, and so the picture to sort of have in mind, I guess, is that, if here's xk, and here's its boundary, the concordance allows you to sort of build a piece to glue onto xk to get xk prime. Okay. Okay, so concordances of this sort of preserve Rasmussen invariance. We're going to use that a little bit later. Another corollary of sort of a general gluing statement that, is much like the original Rasmussen invariant for links in S3 gives you bounds on 4-ball genus. This lasagna Rasmussen invariant gives bounds on sort of the genus function on H2, I guess. So given an element of H2, the genus function for that element is just the minimal genus of some surface that you can smoothly, this is all smooth statements, embed into your manifold the surface that represents alpha, what minimal genus can you find for such a surface, and then, so we get a lower bound based on this S invariant. There's an offset. Okay, so you get a bound like this. There's this extra term, sort of a self-intersection term. I don't want to go into it. This is essentially there to handle the fact that we're talking about smoothly embedding surfaces, but the Skein lasagna needed surfaces that are going to correspond to skeins to be framed. Okay, so this is sort of correcting for if your surface was not able to be framed as it was. You have to do some. You can sort of puncture it to force that framing issue to go to that boundary. I've already said more than I want to. This accounts for framing issues, I guess is. Okay, I don't want to spend too much time on that, or this for that matter, because, I mean, a result like that sort of looks very nice, and it is very nice, but I would claim that, in essence, these sort of results, once you understand like a basic idea of how to glue things together, they essentially follow from Rasmussen's arguments. Okay, there's somehow, not that many new ideas in statements like this. Okay, you sort of get them not quite automatically, but from things that Rasmussen already was able to show about links in S3 and cobordisms between such links. So instead, and maybe what I want to emphasize is that, statements like this are, just like for links in S3, statements like this are useless unless you can actually compute the S invariant in like some case, any case. Okay, and that's what I want to focus on now. How do you ever manage to compute it? So the majority of today will be sort of discussing a technique that allowed us to manage to compute this for some two-handle bodies. Okay, so for two-handle bodies, maybe I'll just sort of write it again. Let's focus on the case okay, let me only have one two-handle. I mean, we can do all this stuff for many two-handles, but the notation and all the writing gets much more out of hand. Also, no link on the boundary. And again, we can handle links on the boundary, but it does require more writing. Okay, so let me write it this way. I mean, it's a colimit somehow as the cabling is going infinite, right? I think we wrote it this way. Okay, you're taking cables of K, right? You are also sort of taking fixed points under the symmetric group that permutes the cables. And you are taking grading shifts okay, so this is just writing down once again the two handle body formula. So let's say alpha, okay, if there's only a naught, right, then alpha is just an integer. Okay, and if alpha is negative, it's alpha minus, and if alpha is positive, it's alpha plus. Okay, I mean, another way of thinking is this: whatever alpha is, if K was this, then the cable is alpha strands that direction, R strands that direction, and R strands the other direction, where if alpha was negative, I actually mean that direction. It's okay? Okay. It's not going to matter too much for us. Sorry. The eraser has magically disappeared. Oh, it fell. Oh, thank you. Thank you. Okay, so, we already know the Lie Skein lasagna module just as a vector space. We really want the filtration levels to be able to say anything useful. And the theorem is that the Rasmussen invariant for the two-handle body, okay, I mean, it's a filtration level of some Lie generator, which is some Skein, okay? In fact, I can sort of compute it from a limiting statement like this. And it's sort of, well, let me write it. Now it's just a limit in the integers. As r goes to infinity, I take the usual S invariant, but with sort of Kavanagh-Wierzanski conventions of these cables. And, well, I have these shifts, but alpha is constant in R. So let me just write this. And then there's minus alpha. And here, there is this extra plus 1 because of, somehow when we defined this one, we had a shift. Okay, what is S superscript R? So this is, let me just, this is sort of the usual Rasmussen invariant for links in S3, but with Kavanagh-Wierzanski conventions. I mean, yes, you know, if you were to build this, you sort of say things in terms of foams. But in fact, you know, you have a similar formula where you're only going to take sort of the oriented resolution of the link, in which case your resolution does not need any webs. Maybe we can talk about it later if you want to sort of think about it more. It may also be helpful just to say, okay, if you don't like these Kohanov-Rosansky conventions, we can convert it to the old one. So let me write, well, you know, in the usual conventions, quantum degrees or Q filtrations are sort of negated compared to what they were. Okay, and so if you want to compute this in terms of the usual S invariant that maybe you're more used to, it's the S invariance of the mirrors and then the, let's see. So there's a shift by the writhe as well. So well, okay, no, let's I mean, the writhe really isn't changing as we change R. So really, it's the writhe is sort of the base case, the R equals 0 case. There's also a shift. Oh yeah, this shift. So this part was essentially just fixing this, and that is still there. Okay, so if you want, you can sort of compute this as limits of usual S invariance. Great question. So am I saying that the sequence will be constant after a while? No. That's the whole maybe issue. These filtration levels can be negative infinity. Okay? And so the question becomes, if you're going to gain useful information out of the Rasmussen invariant, like something useful that lets you actually produce a bound that tells you anything at all, you're essentially asking the question, when do these limits stabilize? Okay. So yeah, let's highlight that for a moment. So let's remember, can be negative infinity only useful if these limits stabilize. And so now the question is, when can I guarantee that? Oh, yes, yeah. Let's see. I mean, I guess that's the point here. The sequences are decreasing. Yes, thank you. So stabilize really is like, okay, well, we were going down. Did we go all the way down to negative infinity, or did we stop eventually? Okay. Okay, all that is okay, but so how was it written? Alpha is a homology class, but if K was a knot, then a second homology class in this two-handle body is just an integer. Okay, so alpha really here is an integer. Okay, let's. Oh, I think I have that over here. Alpha is an integer. Okay, and then alpha minus is just alpha if alpha is negative. We're really just saying, if alpha is negative, I put this many, I put that many cables in that direction, in the opposite direction of K. That's all. Okay. Yes, so, I mean, the notation makes it look more complicated than it really is. It's either in one direction or the other. That's right. That's all. Okay. Okay. I do want to take a couple minutes to say some words about, this is a theorem that I would say is sort of not at all obvious. Okay, if you think about what has happened here, we've somehow, first we had to convince ourselves that in this formula, the canonical Lie generator, like from the lasagna point of view, is being tracked by the canonical Lie generators here. Right? That's not so hard. I mean, we didn't really present to you sort of, how the two-handle body, like where this isomorphism comes from. But if you track through that, you will see that something like this happens. Okay? Except that we're also saying that in some sense you can just ignore this. Okay? And is there something small I can write about this? I mean, so let's let me write. Now, let me just try to say it out loud, okay? So if you have sort of, the proper sense of a Lie generator in here, which, if it's some kind of Lie generator according to some orientation, but then you symmetrized, which is somehow saying, okay, I checked what all orientations could I, given my fixed orientation, I then see what all other orientations I could get from this symmetric group permutation, and I sort of sum over all those Lie generators. And then I have some kind of symmetrized Lie generator. And I ask what filtration level was that in. Okay, and what I want to emphasize to, and why, it really is a theorem and it takes some work, that filtration level probably is different from the filtration level of just a single orientation, which is what this is tracking. This is the filtration level of some single orientation of this. Okay? And so the proof of the theorem does require, these things are the wrong answer at finite stages. However, if one of them goes to negative infinity, the other one goes to negative infinity. And likewise, if one of them stabilizes, the other must stabilize and must stabilize to the same number. Okay, that was all to say there's work here. Okay, and it really relies, I should really sort of point out, I'll write this one, that proof relies on sort of earlier work of Chu's. This is sort of analyzing filtration levels, or maybe analyzing the Lie homology of cables, as symmetric group representations. We had to sort of have knowledge of the actual symmetric group representation theory here and how that affected filtration levels. Okay, so yeah, there's work behind this. Okay. Okay, but if you will believe this formula, then we have sort of reduced to this question that I wrote at the end, which is, when does the limit stabilize? Okay, and let me just say out loud first, if you have some experience with Kolanov homology or Lie homology and things, I think you know that as this cabling is growing, computations get out of hand sort of very fast. Okay, and so our sort of, in my opinion, main theorem of the paper is essentially working out the easiest sort of case one could hope for, okay, is not just when does it stabilize, when is it constant? When does it stabilize right away? I don't want to have to try to figure out, oh, it eventually stabilized. I just want to say it never changed. Okay. And here's the answer. So again, for a two-handle body with a single two-handle, if the framing of your attachment is less than negative twice the number of negative crossings, okay, let's just say phrase in terms of having a diagram. Then the Rasmussen invariant for the alpha equals 0 case, okay, which, if you think about it, is sort of the balanced case. The cables are balanced in the sense that there's the same number going up and the same number going down. This is 0. I mean, I claim that this is more information than saying it was negative infinity. Maybe not that much more information, okay, but, okay. And then let me not write like the precise statement, but as soon as you, well, not as, there's a little bit more to it, but once you know this, okay, you also know something about, the Lie module as a filtered space now. Okay, and that allows you to conclude something about the Kolanov module as well. So, no, I think we were using the notation 2. Let me just say, this thing becomes partially computable. You can learn, in particular, you can learn that it's not 0. Okay. So the question was if the.
So you're able to compute the S invariant, and not like the stabilization only holds for the S invariant, but somehow for the scheme of any one.
Okay, maybe that's not the best thing to say. I mean, so what do we say? We at least know that this limit stabilizes in certain homological and quantum gratings. Okay, and that's I don't want to write it precisely. Okay, somehow if we know that this limit stabilizes, we know something about what homological grading was being tracked by these Lie generators, and then we can say something about that homological grading. All right. We'll talk about it in a minute. The question was, why did this happen? And the short answer is there is no short answer. It's quite complicated. Okay, but I do want to illustrate it. Okay, this is absolutely what I want to spend, a little bit of our time on. Okay, but I'm actually not done with the statement because I think it's fair to say, you know, okay, some S invariant was 0. That's nice, but you know, maybe that's not going to help you actually bound anything. Or in particular, if all you ever know is that my S invariants are 0, I'm never going to be able to tell anything apart. Okay, so I really want a computation where I get some non-zero answers for the filtration level, not just for the module. And so if in addition, you're not, and again, I think about, you know, you have a way to draw it as a diagram, is positive, or you were able to draw it as a positive diagram, no negative crossings, then this is really just saying the framing was negative. Okay, then we also have, in that case, we also have for the case alpha equals 1, so this is sort of, you know, I mean, it's almost balanced. There's one extra strand going the direction of the k. Okay, let me get the okay, in this case, you actually just recover the quote-unquote usual S invariant, but in Kavanagh-Brzezinski conventions, so let's switch that over to the usual one. Sorry, this minus S of minus k for a knot is just no. Sorry. I mean, it's, you know, if k was a link, this is minus S of minus k. Okay. And then, yes, there's always a shift by framing. But don't forget, you've assumed that the framing is negative, so this is some kind of positive shift. Okay. And I guess I'll say and, I mean, the same sentence, but for alpha equals 1. Okay, so
In the two-handle attachment formula, I somehow remembered that the offset of the cables in one direction versus the other is determined by the framing of the knot, but now it seems like it's determined by alpha. Is that right, or am I totally losing it?
So the question is about the offset of the offset of different directions of the cabling. I claim this is determined by alpha, which is the second homology class, which is sort of, you know, in the two-handle attachment is some kind of count of, okay, how many sort of co-core disks were there, okay? But then you always have the ability to sort of introduce two oppositely oriented such disks, and that's what sort of puts in the balanced part. In no sense should this depend on the framing of your knot. Have I answered your question? Yes. Okay. Okay. All right. So I do want to try to present somewhat of an outline of this proof because this is somehow well. Does this give better genus bounds than the regular S invariant? I guess I would say no, but it's a weird comparison that you're trying to ask, like in the sense that, okay, this will give genus bounds for surfaces in some two-handle body. You know, the original Rasmussen, but the bound it's going to give you is essentially equivalent. I mean, it's literally, you know, the same computation. Yeah, right? But the original S invariant didn't know what to do with two-handle bodies. The original S invariant only knew what to do with, you know, sort of surfaces in a four-ball that were sort of bound in K itself, K just in S3. So it's just a somewhat different kind of genus bound that you're producing here. And so maybe the correct thing to say is the Rasmussen invariant. What this theorem is showing is that the Rasmussen invariant actually manages to bound both. It manages to bound genus.
Alpha equal 1 is really like the thing goes 1 over angle, so it's really the genus or whatever lived in. Yeah, okay.
Yeah, do you have a comment on it?
In this case, we are getting a better bond than the Rasmussen invariant. In the sense we are bounding a shape genus.
A shape genus.
Yeah, so for the recording, she sort of pointed out, in fact, for this you're getting a bound on shake genus, not just genus, if you want to view it this way. Okay, let me try to outline kind of. So I'm gonna get this backwards, but shake genus is, in some sense, is essentially the genus function in the two-handle body, as opposed to the genus on just the sort of the four-ball. But I don't know, Chuyu, if you have like a better answer than this.
That's just it. So
Yeah, that's.
if you have a slight surface for K, you can always cap it off using the core of your two-handle. And that closed surface represents the class 1. But conversely, if you have a surface representing class 1, it may not come this way. And the minimals. The shape genus is just a genus function for this two-handle body in that class 1, and it can, in general, be smaller than the size 1.
Okay, thank you. So, okay, yeah, I really want to talk about this for a moment. So we have cables like this. Okay, so the framing, I've already erased the statement of the theorem, but the framing being less than -2 times the number of negative crossings. Okay, once you sort of account for sort of the rise of the diagram, that's the same as saying if I sort of do this diagrammatic cabling, I have less than the total number of crossings, well, negative the total number of crossings worth of twists. But okay, so K is some negative number. So what we did last time for the vanishing result was sort of positive twists. Okay, negative twists have the opposite sort of crossings in them. So let's just point out the sort of crossings in here are like this. And these crossings induce this sort of, define this sort of complex. Okay, and there are shifts in here that I'm ignoring because I'm just not going to write it all. Okay, the crossings like this in this negative twist. Okay, so let me say it this way. What is this framing assumption by you? Like what does it allow you to sort of conclude? Okay, it's not like some kind of easy conclusion, but maybe you can believe me that it lets you conclude that somehow sort of the maximal homological grading present, okay, the maximal homological grading with non-zero homology, it wants to be, according to the twist, it wants to be based on these resolutions, not on these resolutions. Okay. Sorry, yeah, okay, it wants to be based on these resolutions, not these resolutions. And in some sense, saying that I have more twisting than I have crossings over here is saying that this wins out. These resolutions, they still have crossings like left in here. Okay, but these resolutions, like if I have turnbacks like that, I'm able to sort of pull through and get rid of crossings over here. Okay, the assumption is some way of like, there's a precise thing to do here, but essentially you're saying that the crossings in here sort of win out, and the maximal homological degree available is actually 0. Okay, this is for alpha equals 0. When alpha equals 0, I'm looking at crossings sort of like, one of them was up, one of them was down. So this is the oriented resolution. Okay. Okay. I'm sorry. It was even like asked a minute ago. This is really supposed to be a web, right? Okay. The unoriented resolution is some kind of web. Okay. But in fact, the assumptions are being built so that I don't have to pay attention to the webs. It's really everything is happening here in the regular pieces. Okay. The same is true for alpha equals 1 if k is positive, because if alpha is 1, then there's actually odd numbers of strands, or odd cablings. Okay, but they are still balanced in the sense that I can still make the same claim, except when I send all these turnbacks through the cabling, I am going to be left with at least one strand over here. And so I do have to make sure that my remaining crossings over here don't sort of interfere. And that can be done if k is positive. Okay. So that's sort of the first thing, and that's sort of where, why you might expect some kind of assumption like this. I mean, there's a little bit more, but that's sort of the first step. Okay, so this means I'm just going to only pay attention to this homological grading. Okay, everything else about it is very complicated. I'm not going to compute any of that. Okay, because this homological grading is also where the Lie generator lives. The Lie generator is supposed to be based on the oriented resolution. Okay, so great. I'm in the one place where I know the Lie generator is, and I know it's maximal in terms of homological gradings. Okay. No, oh, I'm sorry. Okay, so the question was, in the vanishing result, I defined sort of this mixed grading Q plus H, and I was doing things with that. That is not coming into play here. I am not using the mixed grading. I'm just not writing grading shifts at all. Maybe I'll just sort of say plus bigrading shifts here. I'm just not writing them down, but they are there. Okay, and they are sort of being tracked to decide this about specifically the homological gradient. So yeah, is this the right time to say it? Oh, we're out of time. Okay, so this is one part of the puzzle. Okay, the other part of the puzzle is essentially that, well, we don't have enough time for the puzzle. I'm sorry, guys. I do want to just say that there's a giant combinatorial game where you actually have to sort of check all of these resolutions. I mean, there's a lot of crossings here, and you sort of just have to go through and count what all can appear and what all sort of, how many generators can you get out of all of them. And it's a sort of long and involved game, okay? But let me just sort of, you know, many combinatorics. And so to end sort of quickly, the main example where you can actually apply this and learn something is the knot -5,2, the mirror of 5,2 with framing -1. Well, -5,2 is positive. I can do all this, and I get 3. Meanwhile, the pretzel knot with framing -1. That is not positive, but it's slice, which is to say I can find a concordance to the unknot. And concordances, or maybe I can find a framed concordance to the -1 framed unknot, which tells me that the S invariant here is the same as the S invariant of the -1 framed unknot, which is 1. So not equal, but these are homeomorphic, but their S invariants are not equal, so they are not diffeomorphic. It's an exotic pair. This pair was known previously, originally shown by Akbulut, but here's a proof with a lot of ellipses that we can show they are not diffeomorphic using, in some sense, nothing but combinatorics. Sorry for going over time. Thanks, guys. Yes.
So the main result give like a complete answer to the shape genus of any positive, right?
Say it again.
So the main result, so in particular part, so that means if you have a positive knot,
Yes.
you take the trace, you consider the minimal genus generating the homology class. That's complete. That just equals slice genus and just can be
So
diagrammatic. Right?
yeah, is that right? I mean that's. Yes, but that is the case that, you know.
So that was implied by the theorem.
Yeah. So for our theorem, yes, the framing has to be negative, and so I guess the question is our theorem saying that this?
Oh, zero. Oh, sorry. Okay, the framing has to be negative.
Yeah. So yeah, that's.
Are you doing? Okay. You're not taking trace.
I mean, I'm. XK, yeah, I mean, is sort of, you know, the knot trace, but with negative framing on the knot. But the knot was positive, so I'm not sure. Yeah, K is a framed knot, but the framing is negative. The knot was positive, and then we have a statement. Sort of like this X torsion order that,
Yeah.
yes.
So it's, right, I don't know if that would be sort of, maybe the package for radical boundary, but still makes sense to look at it in the lasagna model, right?
I would believe so, but I mean, somehow you would. Okay, so you would have to. This is actually maybe somewhat important. Okay, if you just say to yourself, I know of some sort of quantity that about Kavanagh homology that I can just sort of take the limit of in this sort of cabling formula. Okay, that's sort of not good enough. Like, you need to know that it corresponds to something about the lasagna. I mean, the lasagna is the thing that's sort of well-defined, and properties of the lasagna module are sort of, in particular, like, I don't know. The better answer is I'm not sure what there is to be gained from this, and if you want to talk about it, we can sort of talk about it out there. But we are sort of out of time, so I think I should cut it off here. We can talk more anyone outside. But yeah, thank you again.